Next. So next we'll be discussing something called as pipelining and scalar operation. So what is meant by that? So pipelining and superscalar operation. Okay. So let us consider this instruction: add R1, R2, add R1, R2, R3. So what this instruction will do in the sense it will add R1 and R2 and it will store the result in R3. It will add R1 and R2 and the result will be stored in R3. Okay. So here with this instruction, let us further understand pipelining. Okay. So now ALU is going to add, arithmetic and logical unit is going to add. So other part of the processor will be free during that time. Okay. So while R1 is getting added to R2, during this time, the processor can read the next instruction from the memory. Okay. So what happens in the sense, while addition is going on, during the same time, next instruction is also fetched. Next instruction is also fetched. This is happening parallelly. Okay. So this is one step. Next step, while writing to R3, finally the result will be returned to R3. So when the result is returned to R3, when the result is returned to R3, during that same time, the operands of the next instruction can be moved to ALU. Okay, because next instruction you fetched already. Now after that you have to decode and fetch that data for that instruction, and that data can be moved to. So move the data of the next instruction to ALU. Okay, the next instruction, the data corresponding to the next instructions can be moved to arithmetic logic. Okay, so now what happens? See when the add is happening, when the first instruction is adding, you are fetching the next instruction. When the first instruction is storing the result, during that time, the data corresponding to the next instruction is moved to arithmetic logic unit. Okay, so this is called as pipelining. This is called as pipelining. So this is possible if you have a sufficient number of functional units to perform these operations. Okay, if you have sufficient number of functional units to perform this operation. Okay, so now what happens in the sense, the time required, now the effective time is getting reduced. Now the effective time is getting reduced. Okay, so so this also means that instructions need not always execute one after another. Instructions are not necessarily executed one after another. So here actually, in your program maybe this is the first instruction and this is the second instruction, but in internally that is not happening. You are zigzagging the execution as long as the output does not change. Okay, so the processor is allowed to change the execution order also, but only thing it should ensure that the output should not change. Okay, okay. Here there is an important line: the value of S does not have to be the number of clock cycles to execute. Uh, have to be the number of clock cycles to execute one instruction. Okay. So what does it mean? So what is yes? So yes we defined as the number of basic steps required for one instruction. Okay. This is the number of basic steps required for one instruction. Okay. So mm, assume that there are two instructions. Say instruction one. Say instruction one. So this instruction one has two basic steps. Instruction one has two basic steps. Okay. Basic basic steps. Say instruction two. There is another instruction, instruction two. Say instruction two also has two basic steps. Instruction two also have two basic steps. Okay. Now Now the point is, if these two instructions were executed sequentially, let us try to understand if these two executions executed sequentially, what will happen, and if these two instructions executed using pipeline, what will happen. Okay? So if these two instructions execute sequentially, what will happen in the sense? For the first instruction, there are two basic steps. So obviously it needs two clock cycles. Okay. And for the second instruction also there are two basic steps. So it also needs two clock cycles. Now what is the average value of S? That is 2 plus 2, 4, 4 by 2 is 2. S value becomes 2. Okay, okay. So that is what the statement means. The value of s doesn't have to be the number of clock cycles to execute one instruction. Here the value of s is equal to the number of clock cycles uh, required to execute one instruction. Okay, because each instruction needs two basic steps, so it needs two clock cycles. Okay, this is for serial execution. But assume the processor supports pipelining. So as it is supporting pipelining, what happens in the sense, say when instruction one is performing basic step one, the processor is executing the basic step of, I'll call it as BS. BS one of instruction one. Okay. During the same time, the processor may also execute the basic step one of instruction two. Okay. Now what happens? During one clock cycle, you are performing two operations. What are the two tasks? Basic step of one also executed during the same clock cycle, say T naught, and basic step one of instruction two also executed during the same clock cycle T naught. So during T1, basic step two of instruction one is executed, and also basic step two of instruction two is executed. Okay, so 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 this is called as pipeline, right? This is called as pipeline. So when basic step one of instruction one is executed during the same time, basic step one of instruction two is also executed, and basic step two of when basic step two of instruction one is executed during the same time, basic step two of instruction two is also executed, right? So this scenario is called as a pipeline. Okay. So now what is the value of yes? See, mm, in the previous case, when it is executed sequentially, first instruction needs two clock cycles. Second instruction also needs two clock cycles. Okay, but now if you see, both instructions has completed in two clock cycles. Both instruction has completed in two clock cycles because the T naught is one cycle, T1 is another cycle. But during this time, you have completed two instructions. So now what is the value of yes? Yes is the average number of number of basic steps, average number of basic steps required for each instruction. Okay, where what is the basic step? The basic step is how many clock cycles are required. Okay, for how many clock cycles are required for each instruction. Okay, so so in this case, so S is the average basic step needed for one machine instruction. The average basic steps needed for one machine instruction. Okay, so so even though there are four basic steps, but all these four basic steps are are completed in two clock cycles. Okay, all the four basic steps are completed in two clock cycles. So it means that two instructions got executed in two clock cycles. Okay, so how much time it will take? Two instructions. So the point is two instructions completed in two clock cycle. So how much clock cycle will take for one instruction? It is one. So by that S will become one. Are you getting? Two instructions you are completing in two clock cycle. So for one instruction it will take how many clock cycle? Only one clock cycle. So the effective value of S is reducing. But here that is not the case. For two instructions you are taking four clock cycles. So for one instruction how many clock cycles? Two clock cycles. Right? So this is how the effective value of S can be reduced. So that is what this line says. The value of S doesn't have to be the number of clock cycles to execute uh, one instruction. Uh, okay, it may when you use pipelining, the things may change. So pipelining is overlapping the execution of successive instructions. So if the computer is more powerful, then you can execute multiple instructions. Multiple instruction pipelines are implemented in the processor. That is, multiple instructions can be pipelined. So in the previous case, we discussed pipelining two instructions. If you pipeline four instructions, five instructions, then what will happen? Then obviously, yes value will reduce. Okay. So the ideal value for S is 1. The ideal value for S is 1, which means what? Again, go back to the definition of S. S is the average basic steps needed for one machine instruction. Okay, average number of basic steps needed for one machine instruction. So, mm, uh, so where each basic step needs only one clock cycle. Okay, so where each basic step needs only one clock cycle. So if S is equal to 4, and if it is serially executing, in each instruction will take 4 clock cycles. Okay, so the ideal value of S is 1. If S is equal to 1, then it means that each instruction is having only one basic step. If S is equal to 1, it means each instruction is having only one basic step, and by that what will happen in the sense, each instruction will execute in one clock cycle. Because if there is only one basic step, then it will execute in only one clock cycle. Okay, but is it possible practically to have only one basic step? No, that is not possible. But pipelining is possible. By pipelining, what will happen in the sense the effective value of S will reduce. You getting? By pipelining, the effective value of S will reduce. When you execute serially, there may be uh, four basic steps, but you are using pipelining. So when you use pipelining in each clock cycle, you may be executing 2-3 instructions. Okay, so obviously the effective value of S will come down, right? So, the ideal value of S is 1. Practically, that may not be possible, but by using pipelining, we can reduce S such a way that we can make S to approach 1. Right? And the goal is to reduce S. Okay. So, if the computer is supporting superscalar operations with multiple stages of pipelining, I mean with multiple instruction pipelining is possible, then yes, may also go less than one. Okay, very rarely. Then we will see like how to increase R, how to increase the clock rate R. So the clock rate R can be increased. There are two ways to increase the clock rate R by improving the IC technology to make the circuits faster, so that the circuit works faster, and by that you can increase the clock rate. Okay. So when you increase and there is another way to increase the clock rate by reducing the amount of processing done in the basic step. But if you reduce the amount of processing done in the basic step, then the number of basic steps may increase. Okay. So this second option is not an correct option. So then we can say that the only way to improve the clock rate is by improving the IC technology. Okay. So when you improve the, so it is not. So when you improve the IC technology, uh, it means that one basic step can be done in less time. That is what we mean. One basic step can be done in less time. Previously, if one basic step can be done in 2 nanoseconds, and if you increase the IC circuit in such a way that one basic step can be done in 1 nanosecond, then the clock rate is improved. Okay. So by increasing the R, the entire processor's operation also will equally improve, except the main memory. Okay, because compared to processor, main memory is a slower device. Then the speed compensation should be done by using cache. This is how we can increase the clock rate. Then there are two types of computers. One is called as CISC, the other one is called as RISC. CISC is called as the complex instruction set computers, and RISC is called as reduced instruction set computers. Okay. And and the and there is a and these are and there is a trade-off between, and this CISC and RISC can be, what do you call, it can be treated as a trade-off between N and S. What is N? N is the number of machine instructions to execute a particular program in a given round, and S is the average number of basic steps for an instruction. Okay, so previously we discussed that we can bring S close to 1. Okay, even though the number of basic steps per machine instruction may be considerably large. So this point you should understand. I don't know uh, how much you are able to catch it. That is, yes is close to 1. That doesn't mean that the number of basic steps will be equal to 1. No, by using pipelining, the effective value of S will come to 1. Because when you use pipelining, more than one instructions were executed in pipeline fashion, so the effective value of S will be reduced. Okay. So when so S is close to, so you can bring S to close to 1 even though the number of basic steps may be larger. Okay. So it is much easier to implement efficient pipelining in processor with simple instruction set than in complex instruction set. Okay. So there are two types of computers. One is complex instruction set computer, another one is simple instruction set computer. So in complex instruction set computer, what happens in the sense you will have a complex instruction which can, for example, to perform a particular task in a simple instruction computer, if you are using 5 instructions, that can be done by just one instruction in a complex instruction set. But this one instruction will be complex. It may perform several operations. But here that one instruction is split to 5 instructions. You get it? So so when compared to CISC and RISC machine, actually RISC with pipelining will produce better result. Okay, it is much easier to implement efficient pipelining in processor with simple instruction, reduced instructions. Okay, because even though there are 5 instructions, that is S value is 5. That is each instruction has uh, 5 basic steps, but you have pipelining. With pipelining, the effective value of S is reduced. Okay, but here even though you have one instruction, but this one instruction may take more than one clock cycle or 3, 4 clock cycles. So that's what we are trying to say here. Next is compiler. So, so the role of compiler is also crucial in deciding the performance of the computer. So the compiler is the one which translates the high-level language program into machine instructions. So to reduce n, it is to reduce the number of instructions that will be executed in a given round, we need an optimized compiler. So the optimized compiler is the one uh, which produced as reduced machine instructions as possible. So the goal is to reduce n and s. So, but actually, when you see, compiler is not may not be designed for a specific processor. But if you but if you want a high quality performance from the compiler, then the compiler should be concerned about the processor. So it is not that if you write a compiler for one processor, it will give better result for another processor also. No, the compiler that is written for one processor may not give that good performance in other processor, right? So the compiler should be designed for specific processor actually to get better performance out of the computer. Okay. So finally, what we are discussing in the sense, so the performance measurement basically to measure T, the time required for a computer to execute an instruction. But computing with T is not that easy. So whatever we have understood till now, it is not that easy. It involves several parameters. Okay. So the computer engineers and scientists, what they thought is it is better to measure the performance of the computer by using some benchmarks. Benchmarks means what? Already you know that there is a powerful computer. Okay? So there is a powerful computer, PC1. We know, everybody know that it's a good computer. So say all the scientific community agrees that it's a good computer. Now we are manufacturing a new computer, PC2. Okay. Now when you want to compare the performance of PC1 and PC2, just you compare PC1 and PC2. You take some 10 programs. Okay. You take some 10 programs, execute all these 10 programs in PC1 and calculate how much time it takes, and then execute in PC2 how much time it takes, and then you can benchmark with respect to PC1. What is the performance of PC2? Is it increased or decreased, or is it matching that? Like that. So that is called as measuring the performance using benchmark. So this is a benchmark computer, which we already know. Then compare with that. So how to do that? That we will discuss here. So measuring performance computer using benchmarks. So there is a non-profit organization called System Performance Evaluation Corporation, SPEC. Okay. They select and publish results for many commercially available computers based on this benchmark study. So for general purpose computers, a suite of benchmark was published in the year 1989. Again, it is modified and published in 1995 and in 2000. And the reference computer used were reference computer is the one whose performance is already known. The reference computer used was Spec 95. That is during the year 95. The one which is published in 95, for that the reference computer used was Sun Spark 10/40. This is the computer name. And for one that is published in 2000, Spec 2000, the reference computer used was Ultra Spark 10. Okay? So let us see how to measure the performance of a computer using this benchmark. It is given by this formula. The spec rating is equal to running time on the reference computer divided by running time under the test. That's it. You take a particular program, say program 1, execute that in the reference computer. That is the standard benchmark computer. Execute in that. Measure the time, how much time it takes. Okay, say time t1, and execute the same program in the new computer which you want to test the performance. And what's the time? T2. T1 by T2 is the spec rating. Okay. So this is a simple formula, and this is generalized like this. So this is for one program, but with one program, you cannot decide the performance. So you take a set of programs. Say we take n programs. Okay, I is equal to 1 to n programs. For all these n programs, calculate the spec rating. For all these n programs, so spec I is nothing but the spec rating of first program. Spec I is nothing but the spec rate of ith program. Like that, you calculate from the first program to nth program, calculate the spec rate, and take the uh, calculate the spec rating for for all these programs, okay, and calculate like this. Okay. So this is the formula given. Okay. So, yeah. So this is how we calculate the spec rating. So this 1 by n is nothing but the square root. Okay. So 1 by n is nothing but the square root. So using this formula, the spec rating can be calculated. Say for example, uh, say for example, for when you calculate spec rate for one particular program, say the reference computer, say say so the spec rating of, for example, if you get a value of uh, 50. Okay, the spec rating value is 50 means the computer under test is 50 times fast as the reference computer. Okay, so that's the way. Right? So that's it about performance measurement. So let us stop here. Thank you.